Hello. Today we start the discussion on electric current. Now, what is a current? A current is made possible by something moving. And of course, an electric current is the motion of electric charges. Now, from your understanding of electric charges so far, tell me, what will make an electric charge move? Well, an electric charge will move when it is placed in an electric field, because a charge placed in an electric field will experience a force. If it has a net force, it will move. Now, how will you produce an electric field? Very simple. All you need is two metal plates, one charged positive and the other charged negative. Is that right? The positively charged object will be at a high potential. The negatively charged object will be at a low potential. There will be an electric field propagated from the positive to the negative. Now, if there is an electric field, tell me, what is the direction in which an electric charge would move? Motion is associated with negative charges. So a negative charge would move opposite to the direction of the field. But remember, our test charge is a positive charge. So although a positive charge will not move, you've got to assume that because it is our test charge, if you place a positive charge in an electric field, what is the direction in which it will, or it is supposed to move? It is supposed to move in the direction of the electric field. So a negative charge will move opposite to the electric field. A positive charge will move in the direction of the electric field. All right, let's now talk more about it. You have seen earlier that a positive charge placed on an electric field will experience a force and move in the direction of decreasing potential. Is that right? The direction of the electric field is the direction of decreasing potential. So a positive charge will move from a high potential point to a low potential point, and a negative charge will move from a low potential point to a high potential point. If a negatively charged metal conductor, for example, if you have a negatively charged plate connected to a positively charged plate, you establish a connection between them externally, an electric field will exist in that conductor. And that electric field will cause the electrons in that conductor to drift opposite to the direction of the electric field. Is that right? The electric field is propagated from the positive to the negative. That means the negative charges in this conductor will drift in the opposite direction. And the drift of electrons caused by the electric field is what we call an electric current. Well, since the free charges are electrons, the electrons in the conducting wire will drift from the negative end to the positive end. While the direction of the electric field is from the positive plate to the negative plate, the drift of electrons take place from the negative to the positive plate. There you are. The direction of the electric field is from positive to negative. The direction of the electron drift is from negative to the positive. The drift of electrons in this way caused by a potential difference. Remember, it is the potential difference between the two electrodes. I'm going to call these two metal plates electrodes. It is the potential difference between these two electrodes that makes it possible for an electric current to flow. That means if I can now have two electrodes. Now, I think I have two electrodes here. If I can have two electrodes, now one on my left is a zinc electrode, one on my right. You see, you will probably look at this as my right hand and this my left hand. So this is a zinc electrode and this is a copper plate. They are both metal plates. If I dip this in dilute sulfuric acid, the chemical action between the metal plates and the sulfuric acid will set up a net positive charge on copper and a net negative charge on the zinc. That means I will now have a negatively charged zinc and a positively charged copper. What will happen if I connect those two externally by a conducting wire? An electric field will be set up. You see that? And a current will flow. Well, let me see if I can show that to you. Here I have a meter that will measure the potential difference between the two electrodes when I dip those two metal plates in dilute sulfuric acid. This is dilute sulfuric acid, and I have the copper plate and I have the zinc plate. Now, when I dip this in dilute sulfuric acid, what will happen? The chemical action between the acid and the electrodes will give a net positive charge to copper and a net negative charge to zinc. That means you will have a positively charged copper electrode and a negatively charged zinc electrode, and this meter is called a voltmeter. What is a volt? A volt is the unit of potential difference. So this meter will measure the potential difference between these two electrodes. Well, these electrodes are now connected to the meter. Is there a potential difference between the two now? No, there is no potential difference. Well, see what happens when I dip it in the dilute sulfuric acid. There you are. It is reading 1 volt. Can you see that? It is reading 1 volt. So this simple arrangement has set up a potential difference between the copper electrode and the zinc electrode by 1 volt. What does 1 volt mean? 1 volt means 1 joule per coulomb. So this setup, the dilute sulfuric acid with these two electrodes, will make available 1 joule of energy per coulomb of charge that is driven in this circuit. Is that right? 1 joule. You see, 1 volt means 1 joule per coulomb. Volt is work done per unit charge. This will make sufficient energy, or 1 joule of energy per coulomb of charge that moves. So here we have now a system that will drive an electric current. Alright, let's develop the concept of electric current further. Now, when the two electrodes that has a potential difference is connected by an external conducting wire, an electric field will propagate through the wire almost instantaneously. In fact, the electric field propagates through the wire with the speed of light as soon as the connection is established, and the electrons drift through the length of the wire. Now, don't confuse with the speed of electrons with the speed of electric field. Electric field is propagated with the speed of light. It's almost instantaneous. And the electrons will then experience the force and will then drift in the opposite direction of the electric field. Now, the electrons do not really move very fast. Now, here I have an illustration of that concept. Now, what I just showed you, the two metal plates with the dilute sulfuric acid, is actually an electric cell, which many of you call a battery. Now, there is a difference between a cell and a battery. You see, what we really see here is an electric cell. It is really not a battery. A battery is a collection of cells. When we use more than one cell, one electric cell, it becomes a battery of cells. So colloquially, we simply call it battery. So what does the battery do in an electrical circuit? A battery produces a potential difference between two electrodes. So this battery has a positive electrode and a negative electrode. There is a potential difference between the positive and the negative electrode. And you establish an external connection by means of a conducting wire. In fact, the one I used is a conducting wire like this. This is a good conducting wire made of copper. So when you establish a connection between the positive electrode and the negative electrode by means of a good conductor, and you can see in place of the meter that I showed you in the demonstration, we have a bulb in here, an electric bulb. So look at the drift of the electrons. The electric field is propagated from the positive to the negative, and electrons drift in the opposite directions. Now, the drift of electrons is rather similar to, let me see if I can find an example. Suppose you have a group of soldiers who are in a circle, and the sergeant stands in the middle and say, "Soldiers, march." Now, what do? Each soldier will be moving like this, is that right? Now, that is analogous to the drift of electrons. The command of the sergeant is the electric field. You see, that triggers the motion. The command, as soon as the command is over, each soldier will begin to drift. In the same way, as soon as the electric field is established, each electron will begin to drift. Electric current. How do we define electric current? Now, that means if you now stay at one point of the conductor, you can see there will be a certain rate at which electrons will be crossing that particular point. So electric current in a conductor like this is the rate at which electrons flow across any section of that conductor. In other words, electric current is the rate of flow of electric charges, the rate of drift of electric charges, or rate of flow of electric charges. And current in a conductor we will represent by I. If you remember when we talked about the thermal current some time ago, we used the same letter I. So when you want to represent a current, we will use the letter I. Now, if a charge delta Q crosses a section of a conductor in a time delta T, then what is current equal to? Well, current I equal to delta Q divided by delta T. Current is the rate of flow of charge. Alright, can you look at this definition and tell me what is the unit for measuring current? Charge is measured in coulombs and time in seconds. Therefore, current will be measured in coulombs per second. Right? And that coulombs per second has a name. It is called ampere. Ampere. Alright? Now, if you know your basic calculus, delta Q by delta T is actually an average rate of change. What is the instantaneous rate of change? Instantaneous current in a conductor is the derivative of Q with respect to T. I equal to dq by dt. Now this is called the instantaneous current in a conductor, and the unit of current is coulombs per second and is called the ampere. It is represented by the uppercase A. 1 ampere is 1 coulomb per second. So if I say there is a current of 2 ampere in this conductor, what does that mean? It means if I stand at this point of the conductor and measure the amount of charge crossing that section, there will be 2 coulombs of charge crossing every second. So 2 ampere means 2 coulombs per second. Alright. Since electric current is caused by the transport of electric charges through a conductor, a knowledge of current I in a conductor will help us to obtain a measure of the amount of charge that passes through the conductor during a given period of time. So, if I can measure the current that is in this conductor for a certain period of time, then I can calculate the total amount of charge that passed through this conductor. Is that right? Because current is the rate at which electric charges pass through the conductor. Since I equal to dq over dt, what is dq equal to? dq equal to I dt. Now, if you want to find the total amount of charge that passed through a certain conductor from a certain time t1 to a certain time t2, what all we need to do is integrate this dq from t1 to t2. That will give me the total amount of charge that passed through that conductor during that time. In order to find the total charge q that passes through the conductor from time t equal to t1 to t equal to t2, we integrate this dq with respect to t from t1 to t2. So q equal to integral t1 to t2 of I dt, where I is given as a function of time. Let's now talk about conventional current. You see, we know that it is the electrons that actually drift when there is an electric field. But remember, for all our studies in electricity, the test charge that we have chosen is our positive charge. Therefore, although, I want you to listen to this carefully, although the electric current is caused by the drift of electrons, the direction of a current is considered to be the direction in which a positive test charge will move. The positive test charge actually do not move. It is the negative charges that actually move. But a conventional current, so although electric current constitutes the drift of negative charges from negative end to the positive end of a circuit, from the negative electrode to the positive electrode of a cell, the conventional direction of current is the direction of motion of the positive test charge, which is from the positive end to the negative end. So the conventional current is the direction of the electric field inside the conductor, because the direction of motion of a positive charge is the direction of the electric field. Now here I have a cell. Well, you know what a cell is now. A cell is a device in which a chemical reaction will set up a potential difference between two electrodes. One will have positive potential, the other will have negative potential, and when you connect the the cell, the positive to the negative externally by means of a conducting wire, then an electric field will propagate from the positive to the negative, causing electrons to drift from the negative to the positive. That means the conventional current will be from positive to negative. So, in the next couple of lessons, several times we will be required to mark the direction of electric current. So what is the direction of electric current? The direction of electric current is from positive to negative of a cell. We will be using an electric cell to produce a potential difference and hence to produce a current. And then you should understand that the conventional direction of the current is from positive to negative. An electric current can only flow in a closed path. If the closed path is broken, the electric current will not flow. An electric circuit can be established by connecting a conductor across a battery. I just showed it to you, and this again we saw it in the last slide. Once you have an electric cell, an electric circuit is established by connecting a conductor from the positive to the negative. Right? That means, now what will be the direction of electron flow? Electrons will flow from negative to the positive externally, and from positive to negative internally. That means actually the flow happens externally through the conductor and internally through the cell. You see, the current has to flow internally through the cell as well. The battery establishes a potential difference between the two ends of the conductor. You see, if I can now connect this conductor, the two ends of the conductor to a cell, one end to the positive, the other end to the negative, what happens? There will be a potential difference between the ends of the conductor. Now, when there is a potential difference between the ends of the conductor, a current will flow in the conductor. So, in order to make a current flow in a conductor like this, what is required is a potential difference between the ends of the conductor. Okay. Now, let's do a couple of examples. A quantity of charge Q passing through a surface of area 2 centimeters squared varies with time according to the equation Q equal to 4t cube plus 3t plus 10, where Q is in coulombs and T is in seconds. What is the instantaneous current through the surface at T equal to 1 second? What is the electric current at the instant when T equal to 1 second? Alright, what is the definition of instantaneous current? Instantaneous current is the derivative of charge Q. Here Q is a function of time. So I equal to dq by dt. Well, you can see Q equal to, I think I need to write that down for you. Q equal to 4t cube plus 3t plus 10. Now, what is the derivative of this with respect to time? The derivative will be, oh, I have it already here. The derivative is dq by dt is 12t squared plus 3. The derivative of 10 is 0. So dq by dt is 12t squared plus 3. Now, the value of this at t equal to 1 will be the instantaneous current at that time. So to find the instantaneous current at t equal to 1 second, we find the value of this at t equal to 1 second. So look at the way I write it. dq by dt when t equal to 1 is 12 times 1 squared plus 3, that is 15 ampere. So at that particular instance, there are 15 coulombs of charge crossing a section of the conductor per second. That is the meaning of this. Okay? Another one. An electric current is given by the expression I of t equal to 75 sine 60 pi t, where I is in ampere and t is in seconds. What is the total charge carried by the current from t equal to 0 to t equal to 1 over 120th of a second? Well, this is the type of current we actually get at home and in the office. In fact, this projector bulb which shines light on me and onto the board is powered by a current given by this expression, 75 sine 60 pi t. Now what is the total charge carried by the current from t equal to 0 to t equal to 1 over 120th of a second in a very short interval of time? Well, you know that I equal to dq over dt, and that is equal to 75 sine 60 pi t. And we need to find the amount of charge that passes through the conductor during this time interval. What do? Well, we find dq equal to 75 sine 60 pi t dt. And we now integrate the dq from t equal to 0 to t equal to 1 over 120, and that will give you the total charge q. Total charge q is integral 0 to 1 over 120 75 sine 60 pi t dt. Can you do this integration without any trouble? Well, that will be, look at this, 75 is a constant. The integral of sine quantity is negative cos of the same quantity, and then divide that by the derivative of this quantity, 60 pi t. The derivative of 60 pi t is 60 pi. You know that integral of sine ax is negative cos ax divided by a. Integral of sine 60 pi t is negative cos 60 pi t divided by 60 pi. And 75 is a constant. And the lower limit is 0 and the upper limit is 1 over 120. Now we replace t by the upper limit and then minus, replace t by 0, and that will give you this value. Can I leave it for you? Can you do that on your own? Well, let me show you how that happens. For the upper limit, when you replace t by 1 over 120, this quantity, I'm going to write that upper limit here. That will be negative 75 cos 60 pi t is 1 over 120. That is the upper limit, minus negative 75 cos 60 pi times 0 over 60 pi. There is an over 60 pi there, over 60 pi. And if you look here in the first term, the 60 and 120 goes, leaving a 2 on the denominator. So this will simplify to pi by 2. And tell me, what is cosine of pi by 2? Cosine of pi by 2 is 0. That's why our first term is 0. Minus, when the time is 0, 60 pi times 0 will be 0. What is cosine of 0? Cosine of 0 is 1. Therefore, this quantity is negative 75 divided by 60 pi. So, what we have, the value of this is 0 minus negative 75 divided by 60 pi. And of course, the two negatives become positive, and that will be 5 over 4 pi. The amount of charge that passed through that conductor during this time interval is 5 over 4 pi coulombs. I should have written that unit. Now you must add that there. That is 5 over 4 pi. Well, I have it there. It is approximately 0.4 coulombs. Okay, another one. The current in a wire varies with time according to the relation I equal to 2t minus t squared. Calculate the amount of charge that passes through the conductor from t equal to 0 to t equal to 0.75 seconds. The same kind of problem. We have dq over dt is I, and I is given to be 2t minus t squared. Therefore, dq equal to 2t minus t squared dt. And what do? Integrate this from t equal to 0 to t equal to 0.75. The total amount of charge that passes during that time interval is integral 0 to 0.75 2t minus t squared dt. Alright, tell me, what is integral of 2t dt? Integral of t dt is t squared over 2. So the first term will be t squared minus integral t squared dt is t cubed over 3. So that will be t squared minus t cubed over 3. Lower limit 0, the upper limit 0.75. So replace your t by 0.75 for the upper limit and replace your t by 0 for the lower limit. That means both these values will be 0 when t equal to 0. That means you can ignore the lower limit. Only the upper limit give you any value here. That will be 0.75 squared minus 0.75 to the power of 3 over 3. And that is approximately 0.42 coulombs. Okay, we will now discuss a very important law in electric current, electricity, called Ohm's law. Now, what does Ohm's law deal with? Well, you remember, how will it be possible to make an electric current to flow through a conductor like this? An electric current can be made to flow in a conductor like this if we can produce a potential difference between the ends of the conductor. You see, it is the potential difference between the ends of the conductor that will set up an electric field in the conductor. And it is the electric field that then drives the electric current. So, Ohm's law is a relation between potential difference between the ends of a conductor and the current passing through it. What do you think is going to be that relation? What happens when you increase the potential difference? When the potential difference increases, the current also will increase. Is that right? Okay. Well, the rate at which electric charges drift through a conductor depends on the potential difference V between its ends. That means the current I in a conductor depends on the potential difference V. And Ohm's law is a relation between these two quantities. Greater is the difference of potential, greater will be the current through the conductor. The relation between current and potential difference is given by Ohm's law. Now you can actually write down Ohm's law on your own. Current will be directly proportional to the potential difference. Is that right? Or for most conducting materials, the potential drop between its ends is proportional to the current in it. As the potential difference increases, the current also will increase. How do we write that? This statement is what we call Ohm's law, and we can represent it symbolically. How? We have the statement of the Ohm's law is this: V is proportional to I. And you know, in science, anytime you have a proportionality sign, it can be replaced by an equal sign. Is that right? An equal sign adding a constant. And there you are, the statement of the Ohm's law. The potential difference is directly proportional to the current, or the potential difference equal to a constant times current, or V equal to Ri. V equal to Ri is actually the statement of Ohm's law. And there are three important quantities there. This constant R is called the resistance of the conductor. In other words, any conductor offers a resistance for the flow of electric charges. So that R is a measure of the resistance of the conductor, which is a constant for a given conductor. It can change from conductor to conductor, but for a given conductor, it is a constant. So what are the three quantities that is defined by Ohm's law? Potential difference between the ends of the conductor, the current flowing in the conductor, and the resistance of the conductor. V equal to Ri. Now, R is a constant and is called the resistance of the conductor. And R, if you want to solve R from here, R equal to V over I. What is the unit for measuring resistance of a conductor? Unit will be volt is measured, well, potential difference is measured in volt. Current I is measured in ampere. So resistance will be measured in volts per ampere, and it is called the ohm. And we will represent that by the uppercase omega, Greek letter omega. So resistance is measured in a unit called ohm, represented by the uppercase omega. 1 ohm is the resistance of a conductor which has a current of 1 ampere in it when there is a potential difference of 1 volt. So if I can produce a potential difference of 1 volt between the ends of this conductor, and at that time if a current of 1 ampere flows in this conductor, that means the resistance of this conductor is 1 ohm. That is the definition of resistance. And very often a conductor is referred to as a resistor, because it has a resistance. So a resistor, which is a conductor that has a resistance, is represented by the symbol. Look at the symbol we use for a resistor. Remember, this represents a conductor which carries a current. It is called a resistor because it offers a certain resistance for the flow of current. Now this is the symbol for a resistor in an electrical circuit. Well, you want to see a demonstration of Ohm's law? I will show it to you in a minute. Now, what are the things that I need to demonstrate to you the concept of Ohm's law? First of all, I need a conductor. Well, I have been showing you the conductor, which is this. Well, this is a very inconvenient way of using a conductor. In fact, in this box, I have several conductors. Let me show it to you close up. Now, this box contains large number of conductors. Now, when I flip this switch up, I'm using a conductor which has a resistance of 1 ohm. If I now flip this switch up, I'm using a resistance of 10 ohm. I can go to any value. You can see if I'm flipping this switch, what is the value of the resistance I'm using? 400 kilo ohm. This is, now when I'm using that switch, that means there is in between these two terminals, there is a conductor which has a resistance of 400 kilo ohm. Now, when I use this one, that will be how much? 4 megohm. Now, I turn this off. I turn the 4 megohm on. It means if I now connect a cell, if I now connect a cell between these two, there will be a conductor that will have a resistance of 4 megohm between those 2 points. Well, what I'm going to do is I'm going to use a resistance of 2 ohm. You see that? I have turned the 2 ohm on, and I want to make sure that everything else is turned off. Only that 2 ohm is there. Okay, so this is my conductor that has a resistance of what value? 2 ohm. Now, what do I want to do? I want to set up a potential difference between the ends of that conductor. Now, what do you do to set up a potential difference? I connect a cell. Now, this is a cell which has a positive end and a negative end. Now, what I'm going to do is I'm going to connect the cell through a control device. This is called a variable resistor. This also is a resistor. You see that? A wire is wound on a frame. This is a very long wire. And this is a conducting wire which has a resistance. I'm using it as a control, because when I move this, I can change the length of that conductor, changing the resistance. So, look at that. My battery connection comes to the variable resistor, and from there, I'm going to connect it to my conductor here, right? And then from the conductor, I'm going to connect it to an instrument that will measure current. Now, this is an instrument that measures current. What is the unit of measuring current? It will be ampere. So this instrument is called an ammeter. An ammeter. So the connection comes to the ammeter, and from the ammeter, where do I go? I go to the cell. And I'm going to make the connection and see if the ammeter reads anything. Well, let's have a look. All the connections are done, and I want to make sure that there is no other resistors on here, as I have a 4 megohm still on. Now, do you see, when I make the connection, I'm making the connection there, there's a current flowing in this conductor. You see, what I have done is, I have connected the cell so that there is a potential difference. I made a potential difference between the ends of the conductor, so that when I make the connection, a current flows. Alright, I also want to measure the potential difference between the ends of the conductor. You see, where I'm pointing are the ends of the conductor. The current goes in here, flows through the conductor, and comes out this way. Now, to measure the potential difference, I connect the voltmeter right across here. Now look at my voltmeter. I had kept it away. Now my voltmeter is going to be connected. I'm going to connect the voltmeter one end here, and the other end of the voltmeter will be connected over here. So I have now a voltmeter connected. Now can you see the voltmeter? Well, let me see if I can raise it up a bit. Well, that is the voltmeter. Okay, I'm going to now make the connection, and you can now see there is going to be a current value and a you see, the ammeter reads the current, the voltmeter reads the potential difference. Can you see those? And now I'm going to use the control. See what I'm going to do? I can change, look at that. I can change the current and I can change the potential difference. Watch this. When I change the current, the potential difference also changes, and I can make different studies based on that. I want you to watch the readings of the ammeter and voltmeter one more time. Now, is it possible for you to read these? What does the voltmeter read? The voltmeter reads 0.5 volt, and the ammeter reads 0.25 ampere. 0.25 ampere. Well, what does the resistance then equal to? What is 0.5 divided by 0.25? Is that 2 ohm? That is what I have put there. So 0.5 volt is the potential difference. 0.25 ampere is the current. Now I'm going to increase the potential difference to, let's see what, I'm going to increase it to 1 volt. All right, I have the potential difference is increased to 1 volt. I think you can read that. That is 1 volt. And now the current is, can you read that? The current is 0.5 ampere. So potential difference is 1 volt. The current is 0.5 ampere. What is the value of the resistance of this conductor? R equal to V over I, that is 1 divided by 0.5, that is 2 ohms. Let's try one more and see if I can make a potential difference of 1.5. Let's see if I can get a potential difference of 1.5. Well, it's about 1.5 there. There you are. That's about 1.5. What is the current? Well, we can actually make any number of studies every time the potential difference divided by the current will give you the value of the resistance. All right. Now, let me see if I can show you a computer animation. Now, this interactive exercise provides a selection of resistors. Look at this, 1 ohm, 2 ohm, 4 ohm, 8 ohm, 16 ohm. These are the available resistors. And you have cells that will provide a potential difference 18, 36, 54, and 72 volts. We can set up this circuit, and this circuit has a switch on off. It contains a bulb. The maximum current the bulb can take is 3 ampere. And this is the cell, and you can put the resistor here. You can create a potential difference by using the cell there. Now, tell me, I have a cell that will provide a voltage of 18 volts, and I have used a resistor of 8 ohms. Tell me, will the bulb blow off? Well, actually I need to open that switch, is that right? Well, You can see the switch closing will not blow the bulb. Tell me, what is the current now in this conductor? Well, the current in this resistor will be the same as the current flowing in the bulb. You see, because you remember we talked about series connection. The bulb is connected in series with the resistor. That means whatever current flows in this resistor will flow in the bulb as well. Tell me, what will be the current that flows in this resistor? The potential difference is 18 volts, resistance is 8 ohm. So the current will be V over R, which will be 18 divided by 8, which is less than 3 ampere. So this is a safe current. Now tell me, what happens if I now replace this resistor by this 2 ohm? Let's do that. Let's take that 2 ohm and place it there and move that 8. Now I have now opened the switch. What will be the current in that resistor or in the circuit? That will be V equal to 18, R equal to 2. V over R will be 9 ampere. Will the bulb suffer that 9 ampere? No, it will blow off. Let's try it. Close it. No, it's blown off. Well, you can actually play with this and learn a little more about Ohm's law. Alright, I'm going to close it. I have given you the website. Now, during my lectures, there are a number of very useful websites I have provided. In fact, almost all the web animations and interactive exercises are borrowed from useful websites, which you can access on your own. Alright? As I told you already, the current I in a conductor is measured using an ammeter. An ammeter is connected always in series with the circuit because the current has to go through it and through the conductor. The ammeter is connected in series with the conductor. Now look at a circuit. This is the battery, that's the positive end. This is the negative end. And I have used the lamp as the conductor. Now remember, the filament of a lamp is a resistor. It allows electric current to flow through. At the same time, it offers a resistance for the flow of current. So this lamp is a resistor. And how is it connected? Look at the way the ammeter, the resistor and the battery are connected. This kind of a connection is what we call a series connection. In other words, end-to-end connection until we complete the circuit. The positive end of the battery to the ammeter, the other end of the battery, the other end of the ammeter to the lamp, then the lamp back to the battery. This is a series connection. So an ammeter is connected in series with the circuit, and we use the symbol shown here. Look at the symbol for the ammeter. A circle with an A is an ammeter. Well, in order to measure the potential difference, you see, this is the resistor we have. The current in the resistor is because there is a potential difference between the ends of the conductor. Now what we need to do is, we need to measure the potential difference between the ends of the conductor. So what do? We connect a voltmeter between those 2 points where you want to measure the potential difference. A voltmeter is always connected between the 2 points where you want to measure the potential difference. So a voltmeter is actually connected in parallel. You see that? Now how will you connect the voltmeter if you want to measure the potential drop across the lamp? We want to measure the potential difference or potential drop. Now, does it make sense to call it a potential drop? One end is a high potential point, the other end is a low potential point. There is a potential drop along the length of the filament. How will you measure it? Now this is the voltmeter. You connect it between the two ends of the conductor, and this is a parallel connection. An ammeter is connected in series and the voltmeter is connected parallel to the conductor. Alright, let's do a small problem. A light bulb has a resistance of 240 ohm when operating at a voltage of 120 volts. What is the current in the filament? Well, you have the value of the resistance, you have the value of the potential difference. Therefore, we can calculate the current using the Ohm's law relation. V equal to Ri. Therefore, I equal to V over R. That will be 120 volts divided by 240 ohm. That is 0.5 ampere. Very simple calculations. Let's do a couple more of those very simple calculations. What is the resistance of an electric heater which takes a current of 15 ampere when connected to 120 volt supply? So we have the current, we have the voltage, we need to find the resistance. So we can go directly onto that equation. If V equal to Ri, then R equal to V over I. Is that right? So V is 120 volts, I is 15 ampere, and the resistance of that heater is 8 ohm. Alright? Find the potential drop across an electric bulb if the filament that has a resistance of 240 ohm carries a current of 0.5 ampere. This time we have the resistance, we have the current, we need to find the potential difference. Potential difference is the same as the potential drop. V equal to Ri. So knowing the values of R and I, we can calculate the potential difference. Well, I'm going to stop this part of the lesson here. I'm going to continue in the next part, study on resistance. We will talk more about resistance of a conductor. Alright, I will see you that in a minute.